Okay, so we're going to have a look at how to carry out some different types of rounding using the floor function. And this is a fun exercise, but it can also be quite useful in a proof to have a rigorous way of expressing a rounded number. So if we take a number x and take the floor function of this, basically what this is doing is taking the largest integer which is less than or equal to our value of x. So for example, if you put 5.1 into the floor function, you get an output of 5. If you put something like 5.9 in, instead of rounding up to 6, this still goes down to 5. But then if you were to put 6 into the floor function, you would get 6 as your output. So you can think of this for positive numbers at least as basically getting rid of your decimal part of the number. We get a slightly different behaviour for negative numbers. So the floor function of minus 3.1, this is actually minus 4 because it's the largest integer less than or equal to minus 3.1. So let's see how we can use this to start off just to round a number to the nearest integer. So we want, if we're going to have rounding to the nearest integer, we want x, which is between n minus a half and n plus a half, but not including n plus a half. We want this to round to n, where n is any integer here. And how can we use the floor function to help us get a nice function where we input x and we output n? Let's have a think what happens here. So let's say we've got x between n minus a half and n plus a half. Let's see what happens when we add a half to this. So x plus a half is then going to be between n and n plus 1, not including n plus 1. Then let's think about what happens to these numbers when we apply the floor function to them. This is the interval of numbers which will output n when you apply the floor function to it. So we can say that x plus a half is in this interval if and only if the floor function of x plus a half is equal to n. Then this tells us actually how to round to the nearest integer. You just take your number, add a half to it, and then take the floor function of that, then that will round your number to the nearest integer. So now let's have a look at how to round to the nearest 10 using the floor function. So we want x, which is between 10n minus 5 and 10n plus 5. We want this to round to 10n if we're rounding to the nearest 10. So for example, you want numbers between 75 and 85 to round to 80. So how do we use the floor function here? Well, let's start off using a similar argument to before. So if we say x is between 10n minus 5 and 10n plus 5, but not including 10n plus 5, what happens to x plus 5? Well, this is just between 10n and 10n plus 10. So we can't quite use the floor function yet, but what we could do is we could divide everything by 10. So this is all true if and only if x over 10 plus a half, so 5 divided by 10 there, if this is now between n and n plus 1. So now we see we can use the floor function here because this interval between n and n plus 1, this is exactly the set of numbers which, when you use the floor function on them, you get an output of n. So we can say that we're in this interval if and only if the floor function of our x over 10 plus a half is equal to n. So now we're not quite done because we want our output of this function to be 10n rather than n, but all we need to do here is just multiply by 10 in the end. So you get 10 times the floor function of x over 10 plus a half is equal to 10n. So if you want to round a number to the nearest 10, all you need to do is divide by 10, add a half, apply the floor function, and then multiply by 10. We can actually generalise this argument quite a lot further as well. So if you want to round to the nearest 10 to the power of k, your output is going to be 10 to the k times some number n, and we need an interval which is centred on 10 to the kn. Then we can proceed just as before. If you say x is in this interval, then this is going to be true if and only if x divided by 10 to the k plus a half, when we do our calculation, is between n and n plus 1. So once again, just skipping a few steps here, you end up with 10 to the k multiplied by your floor function of x over 10 to the k plus a half. This is going to be equal to 10 to the kn, which is the output we want from our rounding function there to the nearest 10 to the k. And we can actually use negative powers here as well, or we could even replace 10 to the k by anything. It turns out that this sort of formula, replace our 10 to the k by, you could round to the nearest 25, or you could round to the nearest multiple of pi, anything you like, and this formula should work. This is really interesting. So we'll just have a look at an example to show that this works for rounding for negative powers of 10. So let's say we take 0.5772, we want to round this to 3 decimal places. So if you're rounding to 3 decimal places, this is basically the same as rounding to the nearest 0.001. or to the nearest 10 to the minus 3. So now let's try and use this formula with 10 to the minus 3. What do we get? Well, we put in 0.5772, divide this by 10 to the minus 3, we add a half to this, take the floor function, and then at the end multiply by 10 to the minus 3. So what do we get in the end? 10 to the minus 3 multiplied by the floor function of, when we divide by 10 to the minus 3, this turns this into 577.2 plus a half. So when we add a half to this, we get 577.7. When we take the floor function, we still get 577. So we get 10 to the minus 3 times 577, which gives us our final answer there, 0.577, which is indeed what we would want when we round this to 3 decimal places. So now we'll finish off by looking at something slightly harder, which is the problem of rounding to significant figures using the floor function. So why is this harder? Well, if you imagine we've got two different numbers, we want to round both of these to 3 significant figures. This first one, we essentially need to round this to the nearest 1,000, or to the nearest 10 to the power of 3. Whereas this is quite a small number, and we need to, when we round to 3 significant figures, we end up rounding to the nearest 100,000th, or to the nearest 10 to the power of minus 5. So in order to apply our previous formula, we need some sort of sense of the magnitude of our number. Unfortunately, there's a nice way we can do this. We can use logarithms. So we look at log to the base 10 of our number. So log to the base 10 of 262,144 is around 5.4. And if we look at log to the base 10 of this number, log to the base 10 of 0.001953,125, this is around minus 2.7. And this is useful now because this gives us a sense of the powers of 10 involved in our number. So if we actually look at the floor function of this logarithm, so we look at the floor function of log to the base 10 of the same number, we get 5, which is actually our largest power of 10 which appears in the number. And similarly, if we look at the floor function of log to the base 10 of our decimal here, we get minus 3, which is our largest power of 10 which appears in this number. So this is really useful now because when the largest power of 10 is 5, and we're rounding to 3 significant figures, we essentially need to round to the nearest 10 to the 3. And when our largest power of 10 is minus 3, we're rounding to 3 significant figures. We take away 2 from that, we round to the nearest 10 to the power of minus 5. So let's write out this rule. If we're rounding to 3 significant figures, we basically just need to round to the nearest, it's now 10 to the power of the floor function, log to the base 10 of x, where x is the number that we're rounding, then minus 2 from that. And we can generalize this to n significant figures, so you can check if you like. All this means is we're rounding now to the nearest 10 to the power of, again, the floor function of log to the base 10 of x, our number, then taking away n minus 1. Okay, so what does our final formula look like then if we take a number x and we want to round this to n significant figures? Well, we can use our previous formula now where we're rounding to the nearest 10 to this power. So in the end, we end up with something which actually is quite striking how complicated this is for something that we might take for granted as something fairly simple. So we multiply by this, we take our x, divide by 10 to the same power, so 10 to the power of log to the base 10x, floor function of that minus n minus 1, then plus a half. So this is how we round to n significant figures given any input number x. And if you're not happy about having the log to the base 10 in there, we could also rewrite this using the change of base formula. So log to the base 10 of x, we could write this as ln x over ln 10, if you prefer.